All right, let's get right into it. We all kind of know what a classical string is, right? Think of a guitar string. It vibrates, it makes notes. Simple enough? But in string theory, we have to take that idea and force it to play by the rules of quantum mechanics. And those rules are, well, they're weird. Today, we're going to break down how physicists actually do that and uncover the absolutely mind-blowing secret about our universe that it reveals.
So yeah, this is the big question. What actually happens when you try to merge these two worlds, when you apply quantum rules to a tiny vibrating string? It turns out it's not so simple. This process isn't just an upgrade, it's a journey that unearths some of the strangest, most profound ideas in all of physics. Let's see where it takes us. So when physicists first tackled this problem, they came up with two main approaches. You can think of them as two different philosophies, two different paths you could walk down, both aiming for the exact same destination, a complete quantum theory of a string. And here are the two schools of thought. On one side, you've got the idealist path. It's all about mathematical beauty. You treat every dimension of space-time equally, you make the whole thing quantum right from the start, and only then do you worry about applying the physical rules or constraints. Then you have the pragmatist path, which does the complete opposite. It says, let's deal with the tricky physical constraints in the classical world first, and then we'll quantize whatever's left over. We're going to start by following that first path, the more elegant one. Okay, so we're diving into the elegant route, the covariant path. The whole idea here is to construct this grand, all-encompassing world of every possible string vibration, every possible state, in a way that respects all the beautiful symmetries of space-time from the get-go. You know, the way this works is actually pretty cool. You take the equations describing the string's motion and you basically upgrade them into quantum operators. Then, with these tools called creation operators, you can literally build every single possible way the string can be excited. It's like playing all the quantum notes on the guitar. This whole collection of states has a name. It's called a Fock space. And it seems like we've done it. We've made a complete quantum description. But yeah, there's a catch. A big one. Oh, yeah. It's a huge catch, because this beautiful, symmetric, elegant structure that we've just built has a fatal flaw buried deep in its mathematical DNA. There's a ghost in the machine, and it's threatening to make this entire theory completely meaningless. And the culprit is hiding right here inside this equation. See that symbol on the right, eta high mu? That's the space-time metric. It's the piece of math that tells us time is different from space, and it does that with a minus sign. Because of that single, solitary minus sign, the part of the string that vibrates in the time dimension starts to behave, well, it starts to behave very, very badly. And this bad behavior gives birth to something physicists call ghosts. Now, here's the deal. In quantum mechanics, every possible state has something called a norm. You can just think of it as its size or its length. The problem is, that norm is directly tied to probability, so it has to be positive. But these ghost states, the ones created by that weird time vibration, they have a negative norm. This isn't just quirky. It means the theory could spit out nonsense, like negative probabilities for things to happen. And let's be crystal clear about this. Negative probability is an absolute 100% deal breaker. It's impossible. You can't have a negative 20% chance of an electron being somewhere. It's just physical gibberish. If we can't get these ghosts out of our theory, the whole thing is completely useless. It's dead on arrival. So, what do? We can't just wish the ghosts away. They're baked into the math we've built. The solution is to be clever. The idea is to find a way to declare that even though these ghosts might exist in the mathematical framework, they are not part of our physical reality. We have to somehow tame them. And here's the how. It's brilliant, really. Think of it like a bouncer at a super exclusive nightclub. First, you have everyone lining up outside, the good, well-behaved states and the troublesome ghost states. Then, you bring in the bouncers. These are the constraint operators, the LNs. And the bouncers have one very strict rule. A state only gets into the physical club if, when the bouncer operator interacts with it, the result is 0. It's like a velvet rope. This process meticulously filters out all the problematic ghosts, leaving them stuck outside, unable to influence any real physical measurement. But this genius solution comes at a cost, a completely shocking, non-negotiable demand that the mathematics makes on the very fabric of reality itself. For this whole ghost quarantining trick to work flawlessly, the universe has to have a very, very specific feature. So that's the real question, isn't it? What is this price of consistency? What does the theory demand from us in exchange for getting rid of these ghosts and making sense? And the amazing thing is, the answer isn't something we get to choose.
It's something that is forced on us by the math.
The source material we're looking at even gives us a little spoiler alert right here, because the math is about to tell us something huge. It turns out, to get this ghost removal to work perfectly, we have to fix one of the most fundamental parameters of the entire theory. And there it is, 26. For the ghost to be completely quarantined, for them to have absolutely zero effect on physical reality, the theory is only consistent if it exists in the universe with 26 space-time dimensions. That's 25 dimensions of space and 1 of time. Remember, this number wasn't an input. We didn't pick it. It fell right out of the equations as a requirement. Now, this whole process has another major side effect. It actually determines the allowed masses for the string's vibrations. And it's a mixed bag. The lowest energy state, the ground state, ends up with a negative mass squared. That describes a particle called a tachyon, which is another huge problem. But look at the very next level up. The first excited state is required to be a massless particle. Now that is amazing, because particles we know, like the photon that carries light, are massless. So the theory is starting to predict things that look like our universe, but only if that universe has 26 dimensions.
At this point, you've got to be wondering, right? Is this whole 26 dimensions thing just some weird quirk of the idealist path we chose to follow? I mean, what happens if we go back and try the other way? Let's take a quick look at that pragmatist path and see where it goes.
So, the light cone path. It's a totally different approach. It gets rid of the ghosts right at the start by solving the constraints classically. Now, it has its own drawbacks. It kind of obscures the beautiful space-time symmetries. But, and this is the incredible part, after all is said and done, after you go through all the math, you land at the exact same conclusion. The quantum string only makes sense in 26 space-time dimensions. And this is just the key takeaway, and the source text says it perfectly. When you have two completely different ways of thinking, two totally separate mathematical procedures, and they both lead you to the exact same, very specific, very strange conclusion, you know you've stumbled onto something fundamental. It's not an accident. The number 26 is apparently real, at least as far as this theory is concerned.
And so we're left with this completely staggering thought to end on. We didn't put 26 dimensions into string theory. We just started with a simple quantum string, and the theory itself screamed at us that it needed 26 dimensions to live in. Which really makes you wonder, is this just some mathematical coincidence? Or is the deep, internal logic of physics actually powerful enough to define the very stage on which reality plays out?